Question A5 then from the 2012 Advanced Higher Applied Maths Mechanics, motion on an incline. Now what's it got? A train leaves the station, it climbs a hill. There's a picture of the hill, inclined at an angle of theta to the horizontal, where the sine of theta, I'll put a little note, the sine of theta is 0.1, 1 upon 10. The top of the hill is 100 metres. Above the horizontal, the train's engine exerts a constant force of 120 kilonewtons. Let's just put a little train here halfway up. So it's exerting a force of 120 kilonewtons. Coefficient of friction, and the little note here, is 0.2. And gives the speed of the train. The speed of the train at the bottom is 4 metres per second. And at the top of the hill, it's increased to 10 metres per second. Calculate the mass of the train. Well, if it's accelerated up the hill, there must be an unbalanced force up the hill. There must be a net force acting up the hill. The pull of the train's got to overcome two things. It's got to overcome friction, it's got to overcome gravity, and anything that's left will provide that acceleration. That'll be the unbalanced force. And all these forces, of course, will be acting along the incline. So we're going to take the forces parallel to the plane. So see if we do that first of all. What are the sum of the forces acting parallel to the plane? Now that won't equal 0 because it's not static. It's accelerating. Well, that'll be the pull of the train, which I could have put here, minus the resisting forces. And there's two of those. There's the force of friction, and there's the component of the weight down the hill. So let's put that in. Here's the weight. We'll just extend that a bit. The weight of the train, mg. The component normal to the plane, which of course is what the friction depends on, and the component parallel to the plane, which is the component of the weight that's going down the way. So I can name that part there. That's the normal reaction, and that would be the component, we'll just call that W, parallel to the plane. So that'll be minus the force of friction, call it that, and also minus the component of the weight parallel to the plane. Right, so what are these two bits? I know what that is, that's 120,000. Well, the friction will depend on the normal reaction. The normal reaction will be, if that's theta, remember that's 90 degrees, that's 90 as well. That's the complement of theta, so that's a right angle, so that'll be the complement of the complement. That's you back to theta again. That must be theta. So the normal reaction will be, that's adjacent to it, that will be W cos theta. That will be mg cos theta. Now I don't need to work out theta. I can take it from this, from theta. If the sine is 1/10, opposite over adjacent, then this side will be Pythagoras. 100 take away 1 is the square root of 99 for that side. So the cosine's root 99 upon 10. So that means this normal reaction here will be m times 9.8. I'll put it in a minute. Might as well work out the force of friction. Force of friction then will be mu n, which is mu mg cos theta, 0.2, I'll put the m at the end, times 9.8 times root 99 upon 10, which will be the cosine, times m. Which, put into the calculator, gives me 1.950, so 1.95 m. It's difficult to see where the marks come in this. There's one mark according to the marking scheme just for saying you've got the normal reaction, mg cos theta. Can't see an individual mark for this. It all seems to be accumulated together. Let's get the other part. What's the component of the weight? That's simple then. The component of the weight is going to be mg sine theta. So that will be sine theta's 0.1. 0.1 times 9.8 times m. So that's 0.98 m. So the net force that will make it accelerate up the way will be the pull of the engine minus the force required to overcome friction minus the force required to overcome gravity. So now we can get the net force. The net force will be, afterwards we'll just call it F, it'll be 120,000 minus 1.95 m minus 0.98 m. Just put those two parts together. 120,000 minus, adding them together, 2.93 m. We'll just call that F now. Well, put that all up here. So there it is. That's the net force. There's a net force making this accelerate up the hill. So much was used up to overcome friction, so much was used up to overcome gravity. The rest, the unbalanced part of the force, will make it accelerate. As it does, it went from 4 to 10. So now you can equate it. That unbalanced force made it accelerate. From that, you should be able to find the mass of the train. Well, I need to get this. I know this part. I need to get this acceleration then. And I'll get that because I know the initial speed, I know the final speed, and I know the distance it took to get there. I know U, I know V, I know S, I want A, stuva. I'll use V squared equals U squared plus 2AS. I say I know S, I might have to work that out from that triangle. Because the distance up there, that's the hypotenuse. 100 over the distance is the sine of the angle. So that distance will be 100 over the sine of the angle, which was 0.1. So that means it's 1,000 meters. So I'll just put it all in here. 10 squared is final velocity squared, initial velocity squared, 2 times the acceleration, which I don't know, I'll put that afterwards, times the distance, which is 1,000 A. I can find A from that. So that means I'll have 100, I need to spell it out, 100 minus 16, that'll be 84, and then divide by the 2,000. A will be 84 over 2,000. Now your calculator, just to move the point back 3 places and half it, 0.042 meters per second squared. Now in the marking scheme there was 2 marks for this part, for getting the acceleration. And then finish it off. F equals MA. 120,000 minus 2.93 m is the mass times the acceleration, is m times 0.042. Take that across to join it to make m. That'll be 2.93 plus another 0.042, and put it over here. That'll be 2.972 m will equal 120,000. So m will be 120,000 divided by 2.972. Almost there. Press the buttons and we've got 40,376.85 blah blah blah. Let's just round it off to 40,400 kilograms. I think those were the final 2 marks. There was 2 marks there, 2 marks there. So the first 2 marks must have been for finding those 2 components, the friction and the component of the weight down the incline. Now, we could have done it a different way. Instead of that, instead of working out acceleration and so on with the net unbalanced force, you could have equated work done with the gain in energy. But you'd have to be careful. Gain in which energy? Which work done? Because as this engine works to pull that train up the hill, it's doing work against friction, it's doing work against gravity, and it's doing work to accelerate the train to increase its kinetic energy. So which ones are you going to include? For instance, don't use the net force of friction and weight and say, oh well, that's provided the change in total energy, and include potential energy if you've already included the work done against its weight to begin with. No, you'd have to think, which bits are you going to use? If I was to use the net force the same as the previous part, I've already included the work it did against gravity. So that net force would only do work to change its kinetic energy. So you could do it that way. You could say this then. Well, I've already worked out the net force. That net force from the previous one, remember the net force was the pull minus the force required to overcome friction minus the force to overcome the weight parallel to the plane. And that was 120,000 minus 2.93 m. We had that already, that force. So, using work done, the work done by this engine in travelling that distance, the work done will be the force times the distance. That will be 120,000 minus 2.93 m. We already worked out the distance to be 1000. Now that work done, since I've already taken care of friction, I've already taken care of the work done against friction, I've already taken care of the work done against gravity, that work that's been done will simply increase its kinetic energy. That will give you the increase in the kinetic energy. So what is the difference in the kinetic energy? Well, you've got the kinetic energy at the start. That will be a half mv squared. That will be a half of m times 4 squared. You've got the kinetic energy at the end, whoops, the final one. That will be a half mv squared. That will be a half m times 10 squared. So the change in energy will be the difference between the two, which is obviously a half m as a common factor, of 100 minus 16, which is 84, halved is 42m. So now we've got equating them, work done equals the change in energy, means that, oh, now there's loads of zeros this time because of the times 1,000. 120,000, 1,000 minus 2,930 m equals 42m. Bringing that across and adding it on, 2,972. 2,972m is 120,000, 1,000. So m should be 120,000, 1,000 over 2,972, which as before is 4376.85, 40,400 kilograms. What you don't want to do when you're equating work energy here is to say, oh, the net force, and think of the net force after taking care of friction and the weight and getting the work done by that force times the distance, and assuming that that work done will create the difference in the total energy, which would be the initial kinetic energy and the final kinetic energy plus the potential energy, because then you've included that term twice for the work done for potential energy. So either take care of it here, and then the change in energy will simply be kinetic, or if you wanted to do it with the total change in energy, then don't include the weight component. If you wanted to use the total energy, then you would simply say the net force, whoops, would be the pull minus the force against friction. That'll be the 120,000 minus the force against friction, which you got before, which, just to state it again, would be that mu n, the mu mg cos 30. Cos theta, which was that 1.95 m. And then the change in energy would be this. You'd have the energy at the start would be purely kinetic, a half mv squared, a half m times, 4 squared. The energy at the end, the final energy, would have the component compartment, but also the gravitational one, the potential energy. So that would be a half m times 10 squared plus mg, I'll just keep g in, times h, which is 100. Which equals, in this case, 100 divided by 2 is 50m, 9.8 times 100, which is 980m. And that, of course, comes to 16.8m, hardly anything there at the start. So the change of energy then would be total energy at the end, these two parts, I'm not even bother adding them yet, 50m and 980m. Notice the biggest parts working against gravity. Take away the energy at the start, minus 8m. So adding those parts together, 1030, 1022. 1022m. The work done will equal the change in energy. Remember, that work done was just the work done by the force less the work done against the friction. So what have we got here? So what was that altogether? It was this part here, wasn't it? So 120,000 minus the frictional, 1.95 m, multiplied by the distance, which was 1,000 meters, should come to 1,022 m. Get the m's together. So now I've got 120,000 minus 1,950 m equals 1,022 m. Putting those two parts together, that would be 2,972. 2,972 m will equal 120,000. So m should be 120,000, etc. over 2,972, which gives the same answer as before. 40,400 kilograms.